Hello, smart people. So this is our eighth lecture. Most probably, I'm not sure whether it is lecture number seventh or lecture number eight. This eighth on this tensors. So now the today's lecture is on this. If we talk about these vectors in quantum mechanics, right? So you might have come across these vectors in quantum mechanics. So if you define some vector in some three-dimensional space, right? So if you define a vector in some three-dimensional space, we have a vector A. So this is right. So that means we define a vector. So this was x, y is the coordinate, and this was vector A. And these are basically the different components of that vector, right? And these are these A, B, and C, right? So that means this vector, if you write now, so this vector I can represent in some new notation. So that's basically called a bracket notation, right? So I'm using now that is called a bracket notation. तो ये bracket notation क्या है? It is simply that you are representing some vector in some way, right? Like so, it is coming from. So we have this. So this is this simply a bracket, BRACKET bracket, right? So there is no logic, but for your convenience, you can say that this is bracket, right? And we have this bracket. So this is bracket. If you remember that we have this bracket, okay, right? And if you remove this C, तो C को remove करो, right? So remove this C, this cat state represented this one and draw state represented this. So that means our this draw state is okay. Now if you represent these vectors in bracket notation, so before that this bracket notation it was given by one of the known physicists, that is Paul Dirac, right? And he introduced these vectors and he represents these vectors in this kind of a notation, right? So that means if you write now the this cat state of this A, so cat state of A is represented by the column matrix. So this vector and these are the components of this vector, right? So both have kind of both have same information. Like this A vector has same information as these components. This form has, right? So both contain the same information, right? And similarly, if you write now the cat state, Broad state of that. So if you write the Broad state of this thing, so if you write the Broad state of this, so this will be equal to. So that means you are basically changing those column vectors column into the row, right? So this that we can say that this A vector, this cat state of this A vector and the Broad state of this vector, so these are duals of each other, or we can say they're reciprocals of each other. You are taking the complex conjugate of that vector, right? Both lives in the this Hilbert space, right? So if you write now, if you write now, if we have a vector A, so that we have represented by, we can represent it by A, B, and C. And if you write it as that bra notation, so that is equal to A, B, and C, right? So what's our, if you take now the product between the bra state and the cat state, so that's equal to. Okay. So this is simply you are taking this product. It is called a scalar product, or you can say that inner product. Right? तो इसको हम scalar product भी कहते हैं या inner product, because this is simply why scalar product, because it's simply that A dot B, right? You are taking the dot product between the two vectors, right? So the dot product between the two vectors is purely a scalar number. So that's why this product is called a scalar product या इसको inner product भी कहते हैं. And it loses its this directionality, right? So it's just purely a scalar number, right? And you'll find this scalar product, this kind of product. So it has a lot of applications in this relativity, because if you're going from one coordinate system to some new coordinate system, right? Now, so this is also called, okay. So instead of that, if you talk about now, if we talk about now one more product, that means if you take now, so first we take the brass state with the cat state. If you take one first, then cat state, then the brass state, right? So if you take reverse of that, that means if you take this A with that A, okay. So let me define here. So before that, so I will represent some new vector. Suppose. So I will write here. Suppose I have this vector A, so that's equal to, and I will define now another vector, or so this I can define this one B. Okay. Now you take now. So if I define now product in this way, if you define now, let me write here. If you define now this. So this I can write as, because A is our, that's our, that's equal to. So this is our that outer product. So this product is called, okay. So this product is again a vector. But the earlier one, so if you remember that, the earlier one, that this was our purely scalar, right? Because A dot B. But that is our, so this is again a vector, right? So this is one of the main difference between, so earlier one was inner product and this is called an outer product, right? Now, if you talk about now, if we have these unit vectors, so if you have these orthonormal unit vectors, so I can represent also those unit vectors in terms of this bracket notation also, right? So if you write now, so in Cartesian coordinates, in Cartesian components, if you write, uh, so if you write now, what's our I cap? So I cap will be equal to, that will be equal to, right? Because these are unit vectors, so that's why I put here 1 1 1 0 0. Second is 2, that means second component 0 1 0, and third one 0 0, right? Now if you take now the inner product, scalar product between the two unit vectors, because if you remember that we have that I dot I equal to j dot j equal to k dot, right? So that's equal to 1, right? Because these are orthonormal unit vectors, so because a dot I dot I is equal to 1, right? And similarly for j and k, right? So similarly, if you talk about now, if you write now the inner product or scalar product between these unit vectors. So if you write now what's I dot I, So that is equal to, because when you take the this is our cat state of this I. So this 100. If you take it in broad state, so this column goes into rows. So it will be that 100, right? And this is I is same 100. So this is equal to, so that's our I dot, right? Is it okay? Right. Because this is clear, because we have this one with one, so rest will be zero. So this is 1 1 plus that 0 0 plus 0 0. So that's equal to 1. Right? And similarly, if you take j dot j now, so that's equal to, similarly for k dot k, right? Or you can write now, so you can write them this in general. You can write like I can write this as, you can write that I dot j, so that's equal to, okay. And so this is our dot product of an orthonormal this basis in this column vectors I mean to say, right? Because this is our delta ij, so this delta ij equal to 1. Okay, because if you take I dot I, so that's equal to 1, and similarly for j dot j and k dot k. And I dot j will be 0 if I is not equal to j, right? So that's clear. So this is the dot product of this orthonormal basis in column vectors, right? And remember one more thing. So we can have, if you take now the outer product, so this was the inner product, the circular product, और जिसको हम डॉट प्रोडक्ट भी कहते हैं, so you can call it by any name, inner product or scalar product, or you can say that a dot product also, right? So instead of that, if you take now the outer product between all possible these orthonormal unit vectors, right? So that means if you write now, if we have this one with one, right? So if you take all possible, so that means because one with one, two with two, three with three. Okay. So this is called a complete distribution. Okay, so this relation is called a completeness relation, right? So if I write this as, so because we have already calculated, so if you write now one with one, तो ये किसके बराबर होगा? So because our one is, okay, so because one is 100, and if you take it as bracketed, so that will be that row matrix, so 100, right? So this will be equal to, so this will be equal to that 100, and take the velocity of this. So velocity of this is 100. Okay. So when you take their product, so this is 1 with 1 plus 1 with 0, 1 with 1, and 1 with 0, 1 with 0, right? So we can rewrite this as, because so this is equal to, okay. So this is clear because when you take their product, yeah, so this is equal to this two, right? And similarly, if you write now 2 with 2, so just check if I'm right because this is 0 with 0 with 0, 0 with 1, 0, 0 with 0, 0, and now 1 with 0 is 0, and 1 with 1 is 1, and you can check it, right? And similarly, if you write now for this third unit vector, so that is equal to, okay? Now, if you take the combination, because if you take the addition of this, because we define the completeness relation, so if some unit vectors, if some vectors satisfy this relation, so these are called, they form the complete set, or we can say that those are called those orthonormal unit vectors are linearly independent and they spin the space, right? So these form the basis of that unit, that space, right? And those bases are linearly independent and they spin the space, but if they follow this completeness relation, right? So when you take the addition, so that means when you take that, so that's equal to, so when you add up them, so when you add them, so you can get here 100. अगर इनको मैं ऐड करूंगा I will get this thing because this plus this plus this, so that is 100 plus this, so we will get only those diagonal elements will be equal to 1, or this will be equal to, so this is our completeness relation. So from completeness relation it has many properties. तो अगर हमारे पास for example if we have if we know the one component of some vector, so we can calculate the total that vector, so with the help of this completeness relation. Or if you know that, take the reverse of that, if you know the total with that vector, so you can calculate the different components of that vector also. So I will show you in the next slide. So this is our completeness relation, so when it is equal to 1, so those set of these unit vectors forms orthonormal unit vectors form the basis which are linearly independent and they span our space, right? And one more important point is that, so from this completeness relation, so we can write them, because we have this, we can write that any vector can be written as then uh, so this is from completeness relation, because I am saying that any vector can be written as a linear combination of these orthonormal unit vectors, right? So this is what these are called the space of space, right? Any vector can be written. So any vector will define this A. So this can be written as linear combination of these orthonormal unit vectors, because these orthonormal unit vectors they form the complete set, because they satisfies our completeness relation. So when any set of vectors satisfies completeness relation, so we can say that those forms the basis, these forms our basis, which are linearly independent and they span the space. So this is the property following from there, that any vector can be written as a linear combination of these orthonormal unit vectors, right? So this is what I wrote. Now, if instead of that, if you take now the inner product of this first component of that A line, right? So this is equal to, or instead of that, let me write here. Okay, so that's clear because we can write this as plus. Okay, so this one, so this corresponds to J component, right? Because this term, so so if I evaluate this one, so this is our I, or you can write it here. Better is to write here because I need to write here. So you can write this as, or this will be equal to, you can take that A2 out, because 2 is our that second component, right? That G. और instead of that you can rewrite this as, तो इसके बदले में ये भी लिख सकता हूँ और इसको मैं ऐसे भी लिख सकता हूँ. I can write this as 1 with 2. So this will be equal to 0 because following the property of that delta function, so this should be equal to some delta I2, or you can write delta 1 2 because 1 is not equal to 2, so this will be equal to 0. So this is for second term, and similarly हम इस term के भी लिख सकते हैं because this is some delta 1 3, so that's also equal to 0, so these two terms will be equal to 0. So that means we will write here, so this will be I with A, so that's equal to, okay, or which is this component? So this is our AI component because, so that is equal to I with A, okay, or you can rewrite this term as, or this will be equal to that I dot A, I dot A will be equal to, yeah. So this relation indicated that अगर हमें A vector पता होगा, so I can calculate the different components of that vector because I can run from 1 2 3, or you can take the first component, or similarly instead of that, so this gives us the first component. If you know the vector A, अगर हमें, because this is known to us, I is simply that 1 0 0, right? So this, if this vector is known to us, A vector, so we can calculate the first component, means X component of that vector. Similarly, if you take now the inner product with J with A, so you can also write then that J with A vector equal to AJ. And so similarly, you can write for these vectors also. So you need to take the inner product J with that vector, or K with that vector. So that gives us the this second component of that vector AJ and third component of that vector. So that means हमें अगर पूरा, अगर हमें vector पता होगा, so with the help of that completeness relation, we can calculate the different components of that vector, right? Or you can take reverse of that. So reverse you can write now. So from completeness relation, we have this, we have that 1 with 1. Okay, or you can write this as, because alpha is that, so it can be alpha equal to 1 2 3, so it takes all those values, so we can generalize this alpha with alpha equal to 1. So this is again completeness relation, right? So if we multiply this by some vector E, so if you multiply this by, अगर इसको मैं मल्टीप्लाई दिस cat state of that vector करूँगा, if I multiply by this term, so this becomes equal to, you can write that, so this is equal to summation 1. Okay, so यहाँ पे थोड़ा थोड़ा इसको मैं यहाँ पे लिखूँगा, so we can write this as, okay, just check because पहले मैंने आप right hand side ही लिया, then I roll the left hand side. Okay, so if you check this term, so this is our that vector A, because this is our unit vector I, that's 1 0 0 0 1 0 0 0 1, right? So that means this vector A, so that's equal to, so if you remember that, so this term ये किसके बराबर है? So that is I with A is AI, or J with A is AJ, or K with A is AK, right? So that means I can write there. So in general, so I'm saying now this, if we have this vector A, I with A, so this gives me AI, right? So ये किसके बराबर होगा? This will be equal to A alpha then. So I can write there, this is summation over alpha. Okay, because I with A is equal to AI, so this will be equal to A of alpha. तो ये हमें देगा जब हम इनर प्रोडक्ट लेंगे किसमें, between that alpha with A, so this gives me the alpha component of that vector. So that means अगर हम कोई वेक्टर लेंगे, इसको मल्टीप्लाई करेंगे by some component, it gives me that component of that vector. So that means I'm taking alpha with A, it gives me the alpha component of that vector. So this is A alpha, right? Or you can write this as, so A vector will be this one, right? So if you check this, so this is now, that means मैं लिख सकता हूँ, so this is vector A, so that is your summation over alpha A alpha. तो व्हाट डज दैट इंडिकेट्स? तो अगर हम इससे पहले जो हमारा था ये एक्सप्रेशन, यहाँ पे मैंने कहा था कि अगर हमें अगर हमें पूरा वेक्टर, अगर हमें वेक्टर ये पता होगा, सो वी कैन कैलकुलेट द डिफरेंट कंपोनेंट्स सो यूजिंग दीज रिलेशंस, टेकिंग डॉट प्रोडक्ट ऑफ I with that A vector, or J with that vector, or K with that vector, तो वो मुझे डिफरेंट कंपोनेंट्स ऑफ दैट वेक्टर देगा. बट हियर दिस इज इन रिवर्स ऑफ दैट. तो यहाँ पे मैं कह रहा हूँ कि अगर मुझे एक कंपोनेंट पता होगा, so I can calculate the total that vector A, right? So if you know the component, you can calculate the total vector, right? So this is the beauty of that completeness relation. So the important condition is that those set of unit vectors, they should satisfy that completeness relation. Then we can write any vector as a linear combination of those unit vectors. So hopefully you are getting these lectures. So in our next lecture, we are going to discuss about a diagonalization and many more things. So that will be really helpful for you. Thank you very much, and Eid Mubarak to all of you. Thank you.